Now, you've already known how to calculate electric forces between charges since last year, but we've never really discussed why do electric charges cause electric forces, and what exactly is allowing them to apply forces to each other even though they're not touching. And this all comes down to the concept of what we're going to talk about today, electric fields. So let's start off by actually reviewing a field we learned about last year, which was the gravitational field. So let's first imagine we have some gigantic hunk of mass like the Earth here, though really this mass could be any size. And this mass is going to physically alter the space around it due to its creation of a gravitational field. So if I have some empty spot way out here in empty space, there's nothing there. There is no mass there. It's just pure space, nothing, vacuum if you will. Well, even though there is nothing there, there is still a gravitational field at that point generated by the mass, because that field extends to all of space. So a gravitational field is really just a three-dimensional physical alteration of space by a piece of mass, in this case the Earth, that causes other masses to experience gravitational forces. So even though the other piece of mass isn't there, and so we don't have a gravitational force, the original piece of mass is there, and we therefore do have a gravitational field. Now, what were some things we learned last year about how to quantify this? Was one, it is going to be proportional to the size of this mass. If we have a bigger piece of mass, we're going to have a bigger gravitational field strength, or G. Additionally, it is inversely proportional to the square of r, that's separation distance. So just as a reminder, this means this is an inverse square law, which we already talked about briefly, but it's going to follow this inverse square relation. If it's really close, gravitational field is going to be pretty strong. As you get further and further away, it dips down very quickly. And even though it extends to infinity, at infinity and far before that, it's going to be practically zero. So we can ignore it at that point. Now, we can combine all of these into an equation where we have little g, the gravitational field strength, is equal to big G, big M over r squared. And let's remember all of these details. So r is just the separation distance between the center of that mass at whatever point in space we're looking at in meters. The big M, and this is important, is the mass generating the field. Now, right now that makes perfect sense because it's the only mass there, but we have to make sure we're real clear on that later when we're looking at forces. G is the gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. So a real tiny number because gravitational forces are tiny. And G is the gravitational field strength. And notice this unit is newtons per kilogram. Now that's going to be important in a second, but it is newtons per kilogram. And really what it's saying is the amount of force per kilogram I put at this space. And we're really used to using this even if we don't remember, because for instance, I look at the surface of the Earth, well that would be G, big M, and R would just be the radius of the Earth squared. Well, if I want to calculate little g, the gravitational field strength is just 9.8 newtons per kilogram, which is the same thing as 9.8 meters per second squared, the acceleration due to gravity. So let's extend these concepts to the electric field because we're going to see that it's practically analogous. Let's start off by looking at some charge Q. I don't care about the size of it. I don't care about the sign of it. It's just some charge Q, and it will generate an electric field that will go all throughout empty space to infinity. So if I look at some piece of empty space here, there is nothing there, but there will be an electric field there, which we abbreviate with a capital E due to the presence of this charge. So the electric field is the 3D physical alteration of space by a piece of electric charge that causes other charges to experience electric forces. Once again, nothing here, so there is no electric force, but there is still an electric field. Now, if we want to look at a couple of details here, E, capital E, is proportional to the magnitude of that charge. So whether it's positive or negative, we're not going to care about that right now, but if it's a bigger charge, you're going to have a bigger electric field. Smaller charge, smaller electric field. Additionally, it is also an inverse square law, meaning that once again, it gets smaller as that distance increases by a large amount. So if we're very, very close, big electric field. As it goes further and further away, the strength of that electric field dips pretty severely, which is why even though the electric field technically goes to infinity, it's going to be zero far, far, far before that for this specific charge. So let's go ahead and formalize our equation for the electric field strength, which is abbreviated with a capital E. And I'm going to go ahead and tell you, yes, I know it is annoying that the electric field strength is a capital E, because what else is a capital E? Energy. I've seen a lot of people draw it with E with a little arrow over it, which is not technically wrong. That's really technically the vector for the electric field, so it wouldn't be the electric field strength, but if you want to do that to distinguish it, I think that's fine. But this is the electric field strength specifically for a point charge, so we just mean for a circular, spherical piece of charge, no crazy shapes. So the electric field strength in newtons per coulomb, so gravitational field strength, newtons per kilogram, electric field strength, newtons per coulomb, is equal to 1 over 4 pi, this is an epsilon, 4 pi epsilon naught, we're going to get there in a second, times Q, the absolute value of Q, which is the magnitude of the charge generating that electric field in coulombs, over r squared, the separation distance in meters. Now, let's talk about first off this Greek letter here, which once again is epsilon. This constant, epsilon naught, is known as the vacuum permittivity. And this is the specific number for it, 8.85 times 10 to the minus 12 coulomb squared over newtons times meter squared. And you can already tell that since this is an extremely small number in the denominator, it's going to result in a very big electric field without necessarily having a whole lot of charge. But what is this vacuum permittivity? This is a fundamental constant of nature, and really what it's telling us is if I have a piece of empty space, how well does the electric field permeate it? How well does it exist in that space? Now, I've seen this called many different constants. Apparently, nowadays, it's pretty common to just call it the electric constant, which, to be frank, makes way more sense. But for a long time, it was known a lot as the permittivity of free space, the free space being a vacuum. So if you see that phrase, permittivity of free space, vacuum permittivity, it's all the same thing. Don't get confused by that. But one thing I want to notice, though, is that if we look at 1 over 4 pi epsilon naught, well, those are all constant numbers. Like 1 is a constant, 4 is a constant, pi is a constant, epsilon naught's a constant. So why bother having a bunch of different constants when we can just combine them into a singular constant? So let's calculate what that will be. You can stick it in your calculator if you want. 1 over 4 pi times 8.85 times 10 to the minus 12, and you stick that in, and we get 8.99 times 10 to the 9th. And that number should look familiar, because that is practically 9 times 10 to the 9th, which would be Coulomb's constant, K. And in fact, it is Coulomb's constant. This right here is the actual value of Coulomb's constant. We just frequently write it as 9 times 10 to the 9th because we round up. So now we have a better way of writing this. The electric field strength, E, besides being the equation I just described, 1 over 4 pi epsilon naught, Q over r squared, the exact same equation is just KQ over r squared. K, Coulomb's constant, is literally equal to 1 over 4 pi epsilon naught. It is just a simplification of all those other constants put together. So the electric field is a vector at some point in space. So it's going to have both magnitude, which we know is just the electric field strength. If you hear the magnitude of the electric field, it means electric field strength. But it's also going to have direction. And how exactly do we define the direction of the electric field? Well, for a gravitational field, this was pretty easy, because all mass just attracts all other mass. Gravity is only an attractive force, so the gravitational field is just towards whatever the mass is that is generating it. But we have two types of charge, positive and negative, so it's not going to be this simple anymore. Specifically, if we're looking at electric fields, the electric field always, and this is where really we want to focus on here, always points in the direction of the force on what is known as a positive test charge. Now, what a positive test charge is just imagine an infinitesimally tiny amount of positive charge that we just can focus on just to see where the field goes, but it's not going to in any way alter the field because it's so tiny that it really doesn't contribute anything. So that is why it is a test charge. It allows us to test the system without altering it. So first off, if I have a positive charge, and I put a tiny little infinitesimally positive charge here, it's not going to warp the electric field at all, but it's going to zoom away from it because the positives repel. So the electric field from a positive charge will always be away from it, because that is the direction that a positive test charge would go. It would be pushed away. For a negative charge, we just have the flip. For a negative charge, a positive test charge would be zooming towards it because it would be attracted. So the electric field is always toward negative charges, away from positive, toward negative. So let's look at a nice simple example. Let's imagine we have some charge plus 4 microcoulombs that is 20 centimeters away from some point in space. And we want to know what is the electric field right here at this point. Well, this is a pretty straightforward thing to do. We just plug in our equation of the electric field. E is equal to kq over r squared. Remember, E is the electric field strength, not energy. I plug in Coulomb's constant, 4 times 10 to the minus 6 coulombs, because micro means minus 6. I have to change the centimeters to meters, 0.2 meters squared, and I get 900,000 newtons per coulomb, which sounds like a humongous amount, but remember, a coulomb is really big, and electric forces are also really big. So, additionally, this will be specifically 9 times 10 to the 5th newtons per coulomb to the right. And the reason why it is to the right is because this is a positive charge. A positive test charge would be pushed away from it, so therefore it's going to go to the right. But let's take this a step further. Let's say that I add now a second charge, a negative charge of negative 8 microcoulombs that is also 20 centimeters away the opposite side, and I once again want to know the electric field at this point. Well, the electric field from the first charge is no different. So I've already calculated it is 9 times 10 to the 5th newtons per coulomb to the right. But I now need to figure out, okay, well, what does the electric field generate from the second charge at this point? I once again just plug in my numbers. The only thing that's really going to be different is instead of having 4 times 10 to the minus 6, I'm going to have 8 times 10 to the minus 6 because the negative goes away with the absolute value. And I get 1.8 times 10 to the 6 newtons per coulomb. But it is also to the right, because a positive test charge would be pushed away from this positive charge, but towards this negative charge. So both charges are causing a test charge to go toward the right. Now, this is not technically the final answer yet, though, because I want the total electric field from all of the charges in the arrangement. Well, I just need to add them together. That the electric field will just be E1 plus E2, which is 2.7 times 10 to the 6 newtons per coulomb to the right. Now, let's say that this one on the left had instead been positive. Well, then they wouldn't be added anymore. They would in fact be subtracted because these are vectors. They are vectors, so we have to add them like vectors. And because of that, we can either add them together or cancel them out very, very easily based on the arrangement of the charges. Case in point, I changed my situation once again, and I just have shifted the negative charge down to the bottom here, but they're still both 20 centimeters away. They have the same charges. So if that's the case, we notice that if we look at the electric field strength equation, E is equal to kq over r squared, well, Coulomb's constant hasn't changed, the charges respectively haven't changed, and the distance between the charges and the point we're looking at, which is right here, hasn't changed. So for both of these, the magnitude of those electric fields is exactly the same. The only difference is now that the electric field from the negative charge is now pulled downward rather than pulled to the right. And if I want to therefore find the total electric field, well, then I just have to add them tail to tip like I would vectors. I take E1 and I could add E2 right here. This is a right triangle, and I could figure out the magnitude of this hypotenuse, which would be the total electric field strength at that point in space. So I go ahead and do that. I do E1 squared plus E2 squared, and then just take the square root, and we get 2.01 times 10 to the 6 newtons per coulomb at that exact point in space, going down and to the right. And if I want to, I could even figure out the specific angle for that. At this point, it's safe to say that you might be asking the question, okay, we've calculated electric field a few times, that's all well and good. Why do we care? I think it's a pretty good question to ask, is what exactly is the point of this? Well, one, electric fields are, more fundamental than electric forces because the fields are generated by a single object while the forces are the interaction between two objects. But more importantly, the electric field allows us to determine the electric force, I had to fix that there, on any charge placed inside the field quickly and easily. If I have some arrangement of charges, I can determine the electric field for those, and they're not going to change as long as I don't move any of them around. And if I put another charge in there, I can quickly figure out the electric force on that charge no matter what the charge is that I put there. So let's talk about that in a little bit more detail. So let's imagine, once again, we're looking at a gravitational field generated by the Earth. And I have the mass of the Earth, the mass of some object here on the surface, and the radius of the Earth being the distance between the centers of the Earth and this object. And, if we wanted to calculate the gravitational force on this object, the real formal way of doing it is using Newton's universal law of gravitation, which is Fg is equal to G m, usually we would say m1, m2, but I could say capital M, lowercase m, over r squared, where r in this case is the radius of the Earth. Now, okay, that's not really that hard, but if I replace this mass with a different little piece of mass, but it's a different value, well, then I have to go in and I gotta do the whole thing all over again. And that can just get really, really tiresome really, really quickly. So instead, let's go back to our original situation, but recognize that this piece here of this equation, Gm over r squared, this is literally the gravitational field strength. So I can just multiply the mass of the object on the surface by the gravitational field strength on the surface, and boom, I can get the gravitational force, or in other words, its weight. Because that gravitational field at the surface is 9.8 newtons per kilogram. So if I put a 1 kilogram object there, it's going to feel a force of 9.8 newtons down. If I put a 2 kilogram object there, it's going to feel a force of 2 times that, which I believe is 17.6 newtons down. Nice, simple, easy calculations. Goes a lot faster, saves us a lot of time. Same thing is going to happen with the electric field. If I have the electric force, if I want to calculate the force between these two charges, we use Coulomb's law. Fe is equal to Q over r squared, where that's Q1 and Q2, but I use big Q and little q just to keep things distinguished between what's generating the field and what's in the field. But the thing is, if I replace this charge with another charge, well, I got to do the whole calculation all over again. And this is particularly annoying if I have like a bunch of charges around and I have to calculate the force on every single charge every single time and then add them together. It can get real tedious and real hard real fast. So instead, I recognize the fact that this piece here, K big Q over r squared, is just the electric field strength. And I can substitute that in and just multiply the electric field strength at this point in space by the little charge we've placed in that field. So I can have some crazy arrangement of charges. If I find the electric field, I can immediately put a new charge in and find the force by just multiplying that charge by whatever the field strength was. It's a much simpler process. And once again, the unit is newtons per coulomb. So if I put 1 coulomb of charge there, that would be 1 coulomb times, let's say it's 10 newtons per coulomb. So 1 coulomb times 10 newtons per coulomb, 10 newtons of force. If I put 2 coulombs there, 2 coulombs times 10 newtons per coulomb, 20 newtons of force. Nice, easy calculations. So this is ultimately summarizing what we just talked about, that the connection between the electric force and the electric field is that the electric force is equal to the charge we place in the field. This is really crucial. It's the charge acted on by the field in coulombs times the electric field strength of the electric field that we're looking at, newtons per coulomb. Similarly, we could say the electric field strength is equal to the force over that little charge. So let's see this process in action. Let's go back to that situation we already calculated earlier where we had 2 charges, the positive and the negative, and we had an electric field of 2.7 times 10 to the 6 newtons per coulomb to the right. And we want to know the electric force on a 4 microcoulomb charge if I'm to place it there, and on a negative 12 millicoulomb charge if I place it there. So I want you to go and pause the video, try this on your own, come back, let's see how you did. Alright, well hopefully you gave it a go, but now let's kind of go through these one by one. Well, if I want to know the force, if I'm to place right here a plus 4 microcoulomb charge, well I just multiply that charge by the electric field strength. Plug those numbers in, nice and easy, 10.8 newtons, and it would be to the right, because this is a positive charge, it goes with the electric field. So it would experience a 10.8 newton force. Now just to make sure we understand why this is so nice, I was able to do that nice and quickly. Compare that to, if I hadn't known the electric field here, I would have had to find the force between the plus 4 and this new plus 4, as well as between the minus 8 and this plus 4, and then I would have had to combine those vectors together, and I skipped all of those steps by already knowing the electric field. Alright, let's take it a step further and do the next one for the negative 12 millicoulomb charge. Same thing. Q times E, and that Q is an absolute value, so it's going to be a humongous number, 32,400 newtons, but this is really crucial. This charge is going to go to the left. And why is it going to go to the left? Well, the electric field shows you the direction of a force on a positive test charge. So a negative charge is going to go in the opposite way. We really want to make sure we do not forget that for positive charges, they're going to go with the electric field. Whichever way the electric field is pointing, they're going to go that way. Negative charges, they're going to go in the opposite direction. We've got to make sure we keep that straight. One last thing I want to briefly talk about, and we're going to go over this in way more detail in class because we're going to go through a lot of examples, is, well, how do we visualize electric fields? Because we can't see them. So if I want to be able to draw a situation and know, okay, well, where is the electric field? If I could see it, what would it look like? How can we visualize that? And one way we do that is through known as electric field vectors, where we just look at every point in space and we draw the electric field for what it would be at that point in space. So looking here in particular, we have a bunch of different vectors. So I have a positive charge and a negative charge, and the electric field goes away from a positive and towards a negative. So if I had some little positive test charge here, it would follow these vectors and go from the positive to the negative. That should be positive. There we go. Now, a couple things we're going to notice here is that, one, the vectors have different lengths, because the direction applies to the direction of the force, but the magnitude of the electric field is proportional to the length. So we have a really big electric field here in the middle between the positive and negative charge. We have a real tiny electric field further out here. Now, if I look at two positive charges, well, those are going to have, they're going to push any positive test charges away. So here, for instance, I'm going to have a real big positive charge nearby, a big positive electric field nearby. I'm going to have a tinier electric field out here. In addition, I'm going to have a real tiny electric field here in the middle because it's being pushed from both charges simultaneously. So the electric fields are going to cancel out. Now, the other way I can visualize this, which personally I find a little easier to draw, but we need to be able to do both, is electric field lines, where really all I've done is I've connected those vectors together into lines. And one disadvantage of this is that, yes, it shows you the directions nice and easily, but the vectors very easily show you how big is the electric field at certain points, because we can look at the length of those vectors. And for the lines, you can't do that. A line is a line. We can't really tell, okay, well, how is the electric field stronger here than it is out here? And what we can look at is how closely spaced are those lines together. When the lines are closer together, like in this region, we're going to have a bigger electric field, and if we look in this region and we see that they're further apart. We're going to have a bigger electric field in this region where they're closer together. You're going to have less of an electric field here where the lines are further apart. So what are the main takeaways for this lesson on electric fields? Well, one, can we calculate the magnitude and determine the direction of the electric field generated by some system of charges at some point in space? Now, we find the magnitude through the equation E equals kq over r squared, and we can combine those all together in vectors to find the total magnitude, and we find the direction, always remembering that it is away from positive charges toward negative charges. Now, can you determine the electric force on a charge placed in an electric field? Keeping in mind that the electric force is just the electric field times the charge of whatever it is that you put in there, and remembering that positive charges will go with the electric field, negative charges will go against the electric field. And then lastly, can we draw visualizations of an electric field generated by a system of charges, either in the form of vectors or in the form of lines, which once again, we're going to practice in much more detail.